All right, so again, hopefully the live stream stays alive. It's been much better than it was this morning, and we won't have to resort to recording. But today we're looking at the next module, Module 4, which is going to be lists and list-based data structures. We're going to start off by looking at array-based lists. You're familiar with this already because you've used array lists, right? Let me just double check and make sure that we've got good audio here. You're familiar with array lists, so we're actually going to design our own array list. This is not something that you do in practice, of course. You would use array lists, but as an exercise in understanding these things, certainly we're going to need to know how they work, because then we're going to look at linked lists, and then we're going to look at applications of both of these things, including data structures like stacks and queues, right, and decks and stuff like that. The motivation here is that dynamic data structures, like a dynamic array, or a dynamic list, I should say, are much better than arrays, right? Throughout this process, we're going to be leveraging object-oriented programming principles of good encapsulation, good abstraction, and good polymorphism. Encapsulation means that we're going to protect our underlying representation of this list. Abstraction means that we're not going to put any onus on the outside world to know the details of how our list is implemented. They're just going to use it, right? And polymorphism means that we want to design a list so that it's not just for one particular type, but it's for any type, okay? And again, the reason that we want to do this is because we don't want to be stuck with regular old arrays for the rest of our lives. When I create an array in Java, and I create it with a specific size of 10, I'm stuck with that size for the rest of the existence of that array. It can't automatically grow. It can't shrink if I'm not wasting space, right? I'm responsible for a lot of the bookkeeping. If I want to put something in there at an arbitrary space, and it's already being taken, that there's something already there, how do I deal with that stuff, okay? And so the answer is going to be that we want a dynamic list. We want a dynamic list that grows, right? It automatically grows, maybe shrinks, as we put stuff in or take stuff out, right? You can add stuff. You can add stuff without thinking about the details of how it gets added. It just does. We want to support basic operations. For example, with a table, with a database, you're doing basic CRUD. Create, retrieve, update, and destroy. Create in the context of a collection data structure means that you should be able to put stuff in, right? You should be able to create, that is, put stuff into the list. Right? You should be able to retrieve, right? In other words, get stuff out of the list. You should be able to update, maybe. You should be able to destroy, right? Remove items from the list. Right? Update, you might want to replace items. Right? Now, some of this is optional. Now, with a full list implementation, I would probably want to support all of these things in a variety of ways. Let's keep it simple at first, because again, at the end of the day, you're not going to reinvent the wheel. You're not going to redo an array list, a Java array list, but we do want to know how it works, so we are going to support some of these basic operations. Over here, I've got my first attempt. All right, now this is the demonstration code here, where I've got my list and I've created a new list. Right? I'm over here, now we actually need to put this class together. So my first iteration of this is going to be that I'm going to have inside this list, it's represented as an array. So I need an array, private. And what kind of an array should I have? For now, let's go ahead and make it into an integer array. Right? And I'm just calling it ARR for short. You can call it the underlying array, the internal array, whatever you want. You can call it array. I'm just shortening it up to ARR, right? A would be too short, right? Too short. The underlying array, too long. but this is just Goldilocks. Right? Not too hot, not too cold. Right? Array. Okay, let's go ahead and make a constructor for it, because over here there's already the default constructor that's being provided for us, but this is not initialized. So you might be familiar with syntactic sugar that allows you to do this. New integer array of a certain size, say 10, right? You can do it like this, but I'm going to do it inside of the default constructor. So public mylist, right? No return type because it's a constructor. This dot array, ARR, is going to be equal to a new integer array. How big should I make the underlying array initially? If I did this, I would not be able to add things to it, right? If I made it of size 10, though, have I put 10 elements into this array? No, I've just made it into a capacity of 10. I haven't put anything in there yet, right? But if I make it into 10, then I can put up to 10 items in there. What happens when it gets filled up? We'll worry about that in a little bit here. Right? But otherwise, that allows me to create an array. Now let's go ahead and support at least one of these things. You got to start somewhere, so we need to get stuff in there before we can take stuff out. So let's go ahead and add a method to do that. I'm going to keep it simple at first. Public void, right? We're not going to return it. You're giving me an integer to add to this list. I'm not going to give anything back to you. I'll take care of that for you, sir. Right? And go ahead and put it in there. Right? Add to end. We're going to give you the ability to add it to the end. So if you want to add 10, okay, 10's now there. Add 20, all right, add it to the end right there. Add 30, 40, 50, etc. Okay. You need to give me that integer to add. I'll take care of that for you. Now I could do something like this. Array of 0 is equal to x. Okay. The first time you do it, it's going to work, 10. But the second time you do it, where should I put it at index 0 now that there's one element in there? No, I should be putting it at index 1. The third time you do this, I should put it at index 3, right? So 10, 20, 30. So I shouldn't be hard coding this. What should I do instead? Array, or this dot array dot length. Will that work? That's fixed. Right? That's going to be 10. It has a capacity of 10. There's a difference between how much stuff I've put in so far versus how much stuff I could put in. Right? So we've got an idea of a capacity and then the actual size of this list. Am I keeping track? I've got the capacity, of course, is there, dot length. But am I keeping track of the size? Perhaps I should be. Right? Private int size. Now, initially, if you create an empty list, what's its size? 0? Okay. That sounds reasonable. Oh, sorry, not this array, this dot size. There we go. Now I can update this. Where should I put it? If there are 3 elements in there already, then the next one would be at index 3. Size plus 1, so 3 plus 4. Remember, it's 0 index, so 0, 1, 2. It needs to go 3. So this dot size. Okay. What else should I do? Increase the number of items in there. In other words, increase the size. This dot size plus plus. Right? Excellent. Yeah. No? Okay. We'll come back to that. All right. Add to the end 10. Let's test it. 20 and 30. Right? Now, if I just run this, of course, it's not going to say anything. I actually want to know that it's 10, 20, 30. So I need a way of pulling things, but as an interim stopgap solution here, let's make a public string to string method. And what I'll do is I'll create a string builder. SB is equal to new string builder. And then I'll iterate over the elements in the array for int I equals 0, I is less than array.length, I plus plus, sb.append, the ith element, and then append maybe a delimiter here, comma space. Now the last one, of course, will end up having a trailing comma. This is just a quick and dirty version, so I'm going to go ahead and ignore that for now. Return sb.toString. There we go. Is that correct? Let's find out. Oh, of course I need to call it. System.out.println, the list. I would expect 10, 20, 30, but I'm going to end up with 10, 20, 30, and then 7 zeros. Why 7 zeros? That's how big the underlying array is. So, yeah. That's going to be the default. Whenever you create an array, the default is it fills it with zeros. So should I be going the length, the capacity? No, I should be going this dot size. And style tip here, even though if it's not, when it's not necessary, it's generally preferred to use this keyword. Right? Let's run that again. Oh, now I'm only getting 10, 20, 30. And that trailing comma, but we can fix that really easy. -1, and then what do we do? Size, this dot size, -1. I take care of the last one outside of the loop, and yay. Except that works now. What if I had done it over here? Print out an empty array. What's going to happen? Exception. An index out of bounds exception. Right? I didn't call any indexes on 7. What did, though? Inside, we were screwing around with indexes. Right? This is kind of a leaky abstraction in that I didn't give you any indexes. No, the list was responsible for that. The list was responsible for printing it out, and if it's an empty list, I would expect it to print out that it's an empty list, right? This is a leaky abstraction. It's leaked out information that there's this underlying array, and it's screwed up somehow, right? So let's make it so that it doesn't screw up and it doesn't leak that information. What should I do? Okay, if this dot size is 0. Return empty, right? Or some special flag value or something like that. And now when I get this and it's empty, and then it's 10, 20, 30. And if you want to get really fancy, you can put in those square brackets, et cetera, et cetera, et cetera. Right? Okay, good, nice. What if I want to support other ways of adding stuff? Right, just adding it to the end all the time. Before we do that, let's go ahead and test this a little bit more. For int I equals 10, I is less than or equal to 100, I plus plus, or plus equals 10. We'll go up by increments of 10, so 10, 20, 30, 40, all the way up to 100. And what I'll do is I'll add I to the end. Okay. Now, this should work. 10, 20, 30, 40, all the way up to 100. What if I go up to 150, though? Length 10. What happened? We hit our capacity, right? We hit that 10. We originally made it so that it was only 10. This is where we need, now the list, needs to handle those little details, right? Outside the class, they shouldn't have to worry about those details. That when your array gets filled up, expand it out so that it's bigger, so that you can accommodate more items, right? we shouldn't have to deal with that over here in this demo class. We're just using the list. Good abstraction means that the list does list things, including expanding itself out to accommodate more elements. So help me out here. How do I know if I need to expand? If the size is equal to the underlying array capacity. There we go. So resize because it is full. ... All right. How do I do that? I've got an array of size 10 initially, but after this has been run a million times, it could be size X, right? Or size because that's what my variable is called, right? Or it has dot length as its capacity, which is equal to size, so it's the same thing. If it's 10, I need to expand that out, but I don't want to lose those elements. I can't do that with an irregular array. I mean, the whole reason that I'm doing this exercise and creating a list is because with a regular old array, there's no way to expand and contract it, right? So I need to create a new array. Int new array, ARR, is equal to a new integer array. What size should I make this one now? 20? Oh, okay. The old one's length, this dot array dot length, and I could add one, and I would only expand it out a little bit each time, right? There's a cost to this though. If I've got 1,000,000 elements in this array, and I want to make it 1,000,001 element capacity, right? That means I'm copying over all 1,000,000 elements, right? Well, which I haven't done yet, but I will be. So let's go ahead and just slap on at least 10 more, right? Now again, if it's 1,000,000 elements, there's still a cost of copying all those 1,000,000 elements, okay? And that's where we'll get into algorithms and algorithm analysis after this module, right? What are the consequences of that? Now I copy over the other elements, ... Well, that's going to be a for loop. For int I equals 0, I is less than the old arrays, this dot array dot length, I plus plus, for each element in the old array, copied over to the new array. And this dot ARR sub I. There. And the extra space is going to be all zeros because that's the default. Okay. And now finally, make this this lists array point to the new one. So this dot array is going to be equal to the new array. Now that's a shallow copy, but that's exactly what we want. Prior to this line, we had two references, the lists array and then the new array. We're simply making this one point to this one. What about this old array over here? If this were C, what would I have to do? I'd have to clean it up. I'd have to free it. With Java, do I need to worry about that? No. Automatic garbage collection. Nice. Okay. What about this now? It'll work because now if we've got 10 elements in there and we wanted to add it at the end at index 10, well, now it's big enough to accommodate that. So we don't have to change anything, any of the rest of this, this method. Right? So let's try that out again. Yay, now we get up to 150. Can we get up to 1,500? Yep. Can we get up to several billion? Yep. Right. We can probably go as much as the memory capacity will allow us. I'll go ahead and keep it low though, so that when we print it out, it still is readable. All right. Okay. Now what? Break it. I don't know how to break it with just this functionality. Add to the end, add to the end, add to the end. Right?
Put in a string.
Oh, okay. That's a good way of breaking it. L dot add to end. Hello. Well, I broke the compiler, right? Because this is a list of integers only. Right? So hold on to that thought. We'll fix that in a moment here. Doesn't sound too flexible or too usable if you can only ever add something to the end. What other operations might you want to support? Here I've got 5 elements in there already, 10, 20, 30, 40, 50. Maybe I want to add it to the beginning. Maybe I want to add it to the end. Maybe I want to add it and put it right here in between these. What would I have to do with the array though? With these 3 elements, if there are 3 elements and 2 elements, what would I have to do if I wanted to put it right in between? Move these down and make accommodations for it. Okay. Public void add element at index. We take an element x and int index at which you want to add it. Okay. All right. How is this going to work? If I've got 5 elements here and my index is 0, 1, 2, I want to move these guys down so that I make room for it. I could, but then ultimately, if I split it into 2 arrays, what am I going to have to do at the end? I'm going to have to put them back together. So these 5 elements, why don't I just, shove them over? Right? I could start by copying this one over to here, then this one over to here, then this one over to here. In other words, work left to right. That seems really complicated though, because I'd have to put this into a temporary, I'd have to take the future one out, put it into a temporary variable, then move this over, and now I've got my temporary variable. Now I need to put that where over here, and then another temporary variable. That seems really, really complicated. What if I started at the other end? Move it over, move it over, move it over. Now there's enough room to put the guy where I want it to be. Right? So we will shift elements to the, to the right, from the end to the index. Right? Yeah.
Aren't you gonna have to add 0 to the end first?
No. I mean, what do you mean? Is add 0 to the end?
Well, in order for there to be if there are 5 elements in the array,
Right.
And you want to add a 6th one, you're gonna need a spot for that 6th one.
Well, so we do have to consider our capacity, right? If we're at capacity, I can't shift everything down, otherwise that one would fall off the edge of the world, right? So I am going to have to worry about capacity, right? And that's what I was going to do next here. But let's go ahead and do the shifting first. Right? For int I starting where? At the end. So if there are 5 elements in there, I want to move element index 4 over to 5. So this dot, not the length or anything like that, but size -1. All right. While I is something, I minus, I'm going to be moving right to left, so I is going to start back here and then move this way. Okay? And what I'm going to do is I'm going to take this dot array sub I plus 1 and make the next one. Here's my I currently. I'm going to make. I'm going to take this current element, ith element, and move it to I plus 1. So array sub I plus 1 is equal to array sub I. Right. The one ahead of me will become me. Okay. Now, what do I go down until? Right. Move this one, move this one, move this one. That's where I want it to be. So I do want to take care of the indexed element. So while I is greater than or equal to index. Right? That shifts things down. Once elements are shifted down, now I can put that thing where it belongs. So this dot array sub index is equal to x. All right, so a couple more things that I need to be thinking about here. What else? Let's go ahead and try it out first of all. L dot add element at index. I'll just go ahead and add 42 to somewhere in the middle, 5. Okay. And let me kick this down to 100. So 10 to 100 by tens. And then we should expect 42 to be at index 5. So 5 things before it, 10 through 50, then 42, then 60 through 100. So that it doesn't lose anything. Ah. What was wrong?
The last one dropped off.
Right, the last one dropped off because it was already full. Okay. So to accommodate it, what is it going to look like? If it's full, then we need to make it bigger so that we can shift stuff down. Copy. Paste, or should I rethink that before I do that? Yeah, what should I do? Oh.
For the last one, use the function of the method that we just created, and then for the rest of them, do the logic, but I is going to be less.
Ah, so you want one of these methods to call the other one.
Yeah.
I like that idea. Hold on to that for a second, though. Right? If I've got, I'm probably if I have 3 or 4 add to the end, add to the beginning, add to an arbitrary index, et cetera, et cetera, et cetera. All of those are going to be checking capacity and potentially increasing the size, right? So let's go ahead and put that into a method instead of copy pasta. Public void increase capacity. And for that, I will take this code. Excellent. And now I can just call this method. If it were at capacity, then call that. And I'm going to also replace that same code over here in add to end, if the capacity has been reached. Okay, yeah?
Is it possible that you could make the increased capacity like a private?
Oh, you guys are predicting everything here, right? So let me come back over here and suppose that L dot you look and see, oh, I want to use this list now. Wait, what's that increased capacity? What was it? Increased capacity. Oh, what's that? Capacity? Should I be having to worry about capacities if this is a list? Probably not. That's a leaky abstraction, right? It would be even worse if before you add the next element, you need to check to see if I'm full by calling the isFull method. And if I am full, then you need to call this other method on me, right? I'm dictating to you on how to use my interface? No, right? That's my responsibility. List things belong in the list class. List responsibilities belong in the list class. So you're right, this should be private, right? I can call it, but you can't call it because if I gave you that responsibility or if I gave you that ability, that would be a leaky abstraction. Right? You shouldn't have to worry about those things. Okay? Okay. Does it work now? Well, obviously this won't compile now, so let's go ahead and get rid of that. All right. Oh, 42 it worked. 10 to 50, then 42. Did it work? 60 through 90? What happened to that 100? Did it fall off? It didn't fall off because we increased the capacity. But what didn't we do? This dot size plus plus. There we go. And now it works. Right? All right, well, add element at 42. Let's go ahead and add element 43 and 44. Let's do some edge cases or some corner cases, right? Something might happen, I mean, adding it somewhere in the middle of a pre-existing list, we have some evidence to say that that's correct. But some edge cases, literally edge cases in this case, is going to be what happens when you add something at index 0? What happens when you add something at index at the end? How much stuff have I put in this now? 12 items, so the next one would be at 12. Right? That should work. Hey, that does work. What happens when I try to do, I was good at my math there. I added up 12, you added up 12, we agreed, so it must be right. What if I was wrong though? What if it was, I think I put 15 things in there. Wait a second, what happened? Oh, well, here, let me do 45 here to show you that 45 never got in there. Instead, we're, 0 at the end? What happened? How many items are in here? Not 15. Good answer, not 15. You didn't give me a positive answer because do you see a way of telling the outside world how big I am? Nope. So, let's do that. Public int get size. Return this dot size. Right? And let's ask before we put that in how big it is. L dot get size. How much stuff is in there before I put in the element at index 15? Only 13 elements. Right? So we were both right, 12, and then we added another one, 13, and it did get in there somehow. It's just that it didn't get in where it was supposed to be. Right? There were only 12 elements in there, and we wanted it at index 15, leaving a gap in there. It actually is in there because it was within our capacity, but if I put something completely out of bounds, what would you expect now? An index out of bounds exception, right? So let's rethink this now. Add element at index. What's the first thing we should do? Make sure that the index is a valid index. So what is a valid index? Something 0 to be okay, right? So anything negative though, no, you can't do that. So if the index is less than 0, these are error conditions now. What are the bad values of index? So if it's negative, or if there are 5 elements in there, 0, 1, 2, 3, 4, I should be able to put something at 4. Just shove this guy over and now it's there. Should I be able to put something at 5? Yeah, well, why not? That's just added at the end, right? Should I be able to put something at 6, leaving us a gap? Probably not. So if the index is greater than the size, then this is an error. How should I handle this? Silently, return, don't do anything. System.exit with an error code. Kill the entire show just because somebody gave you a bad index, right? System.out.println. You can't do that. ... Yeah, how do we do error handling in Java? Throw a new exception. I'm going to throw a new illegal argument exception. Now, an index out of bounds exception, that's probably, that's what an array list would do. Because an array list, all lists are index-based. They're 0 index-based. So if you ask for something out of bounds, then clearly it's going to throw an exception. An index out of bounds exception is appropriate. I'm showing you that you can throw any type of exception that you want with any message that you want. Index plus index is out of bounds. Right? And then you can put more information in there if you really want to. But now I'm going to get my message instead of that underlying message that Java generates. Index 150 is out of bounds. Right? Would it have been appropriate to force somebody to do error checking over here? Like, before I put this thing in, I need to check if L.getSize is less than 150. I can't do it. Right, or something like that. Right? Should I do error? Should I put that on you, the user that's using me, the list? Should I say you're responsible for error checking, not me? Right? No, list stuff belongs in the list class. Put responsibility where it belongs. In fact, it's in the design, right? Solid principles, S is single responsibility principle. Where do those responsibilities go? They go in the class. So no, we do not expect you to do error checking, but we do expect that if we throw it back at you because you did something wrong, you handle it. Right? And that's what we're doing here. Okay, good. I guess you could also, another corner case here would be negative values. Of course, that would result in the same thing. Index is out of bounds, empty. Oh, weird. Why did it happen there? It's asynchronous. So if I ran this again, I don't think I'd get the same thing. No, I didn't get the same thing. Now it's fine. It just got flushed differently. Output buffers are asynchronous, and when it's their choice on when they get dumped. That's why you can't rely on standard output to do debugging, because the error could have happened. You could have, 50 messages in the standard output buffer, then an error, and those 50 messages, maybe 25 of them get printed before it gets the error airs out and it dies, right? And then you never know. Then you think, oh, it must have happened up here. Nope, it happened down here because that buffer never got flushed. You cannot rely on standard output. And you saw a very rare instance, actually, of Java showing you that happens. It was weird, but that's why I was thrown for a loop there. Like, I'm sure, I shouldn't have done that. I should have used that luck to buy a lottery ticket or something like that. You're never going to see that again. All right, good. What else?
If the index is over the size, would you make the size longer to accommodate that index?
You could. So if there are 5 elements in there, and you want to add an element at index 100, we'll do that for you and also fill in zeros all the way along. That'd be kind of weird behavior, but you could design it so that you would support something like that. Yeah, exactly. One thing I want to do is go back and refactor this stuff. 1, 2, 3, 4 lines of code. Get in the habit of RTMing, especially with something like Java. RTMing in C is useful, but ultimately you're probably going to be pulling in a library, right? And searching around for how do I do this stuff. There's a nice little convenient method here. This dot array is equal to arrays dot copy of, right? What we were doing was we were creating a new array that was larger and then copying over the old array. Copy of, and the original array is this dot array, and you can provide a new length, right? The new length will be, if it's larger than the old length, it'll just copy over what was in the original and then fill it in with zeros. If it's smaller, then it'll only copy the new length is 5. It'll only copy over the first 5, right? And you can do a whole bunch of other tricks and stuff like this with this. But this dot array dot length plus 10. That's basically exactly what we did before, but now it's a one-liner. Right? Excellent. Another refactor that I want to take care of. Shifting elements down, add to end. Now let's go back to your idea of should one of these call the other? Which one is more general? Which one is more specific? This is the more general, right? The index, because you can add it wherever you want, whenever you want. Right? This one is really specific because it's only add to the end, add to the end, add to the end. Right? So we will have the specific call the general. Right? Let's get rid of this. Add to end equivalently can be this dot add at index. What? We're going to add x, but at index, this dot size. And regression testing. If I didn't, I refactored two things. If I would expect the same behavior though. If I get different behavior now, I regressed. I broke something. I didn't break anything. Yay. Right, the same as before. Yeah. Okay. All this testing that I've been doing has been ad hoc testing. Ad hoc, in other words, I type a bunch of stuff, I run it, I look at it. Right? I go change stuff, I type a bunch of stuff, I look at it again. It's ad hoc. Right? It's kind of just, not that type of testing is bad. That type of testing, though, is, well, it's ephemeral, right? It's not repeatable. It's a sanity check, right? As you're designing and implementing this stuff, test it every so often with ad hoc testing here. But in a real project, in a real large project, you would want your tests to be repeatable and automatable so that if you do break something, you can run all the tests again with a push of a button and not have to worry about that. And that's what you do in lab, but we did it all for you, right? That's all JUnit stuff. We want to expose you to proper unit testing, but we also do it for a selfish reason, right? Why do you think I did it? So that to grade, I can hit one button. And that's what I do at the back end. Every week I have to tweak my scripts because each lab is a little bit different. But certainly, now this is why I complained about grading the SQL scripts for the last two labs because those were manual. I had to go through 160 submissions to see, yep, that looks good, yep, that looks good. So it took me several hours. But with the stuff that we have for JUnit, I hit a button, it generates a CSV file, I import that into Canvas, and I'm done, right? And now, I do go back for anybody who got a 0 and just make absolutely sure that the script didn't screw up, but just to give them a second chance. That's why we have computers. We love automation, right? We love being lazy. You should enjoy being lazy. Then you can go off and play. I haven't been playing any video games lately. Something, yeah, whatever. Say what?
Automate, be lazy, save some time to work on something else to automate something.
There you go. Be lazy so that you can have some time to go automate something else so you can be more lazy and more lazy and more lazy. Then eventually, people do that, and then I've seen story after story on Reddit of people describing that, they go to a company where they've been doing, basically manual data extraction and data manipulation and stuff like that, and nobody there knows how to program or script or even, stuff beyond summing in Excel. And they have a little bit of knowledge in scripting, and so they take their normal job and they script it, and then they don't tell anybody about it. You just hit the button in the morning, and what took you 8 hours in a day before has now been automated, and you just sit there and then you play with video games for the rest of the day. Not very fulfilling, but definitely you've earned your 8 hours screw around time today. But and it's actually quite sad that people don't realize to the extent that stuff can be automated if they just hired the right people. That you might think that puts a lot of people out of jobs, right? And yes, in the short term, that automation does do that. Robotics is going to threaten to do that. Right now, self-driving cars are going to put taxi drivers out of. There will not people that are doing Lyft and Uber, right? The taxi drivers complain that they put them out of business. They're next. The self-driving cars will kill that industry. Self-driving cars will kill the automobile industry because once you've got self-driving cars, you've got ride sharing. There's no need to own a car anymore. When you can just order up an automated car that shows up, and then that automated car goes and serves 10 other people after it. Car ownership in the next 20 years, 30 years, when full automation happens, why do I need a car? I can order one up anytime I want. No maintenance, no insurance, no hassle, et cetera, et cetera. No parking, right? I have to pay $150 a semester for parking, right? Now, the thing there is that the price point has to get below what it currently costs to drive a car. But once automated drivers prove that they're better than humans, it will no longer be a question of choice. It'll be a question of you will not be able to afford insurance anymore because insurance companies will only support the machines that do a hell of a lot better job than you because they don't want to pay out for accidents anymore, right?
There would be a truckload of reasons why not to.
Well, not to automate?
No, not to drive anymore.
Oh, yeah. Well, there are plenty of reasons not to drive.
Hot roading your car, having fun with it.
All right, yeah, I do remember you guys like the manual shift, right? So, yes, there will always be a need for recreational driving. You'll probably, unfortunately, end up being restricted, right? If you want to know what the real future looks like, I think there's a movie with the Fresh Prince. He's iRobot. There we go. It was supposedly an Isaac Asimov adaptation, but it wasn't anywhere near what Isaac Asimov wrote. But anyway, he the self-driving cars, they were going 300 miles an hour, right? And getting this close because the automation was so good that they could predict that there's no need. There will be no intersections. There will just be continuous traffic because it'll look terrible. It'll be really, really scary if you're in there. But once they've got it down and it becomes a closed system, you will not be allowed as a human on those tracks anymore, on those streets. So I'm sure that there will be a division of human drivers over here for recreation or whatever you want, and everybody else over here. We already have that to an extent with bikes and pedestrians and carpool lanes and bus lanes get their own lanes, etc. So probably within your lifetimes, you may not have a car anymore. You may not have the option of having a car anymore if things go right.
You have to redo all the interstates and stuff.
Oh yeah, it'll be a huge infrastructure change to accommodate that, but
Hey, there's those new jobs.
exactly. Well, the robots will build the the highways. That's a good thing though, ultimately, because that means I went off on that because again, you think in the short term it does cost jobs, but one, it creates other more niche jobs, but at the same time, individuals' productivity goes up. That means that we just need to figure out another way of spreading out the productivity that remains. If productivity is so high for an individual, there is no reason that we have to have a 40-hour work week. We could have a 10-hour work week among 4 people, still getting the same salary because you're paying for the productivity. You should be paying for the productivity. You shouldn't be paying for the person, right?
Or creative jobs.
Yep. Yeah. Exactly. Like creative jobs. Other things, right? Luxury jobs basically become then a way to make money. Anyway, back to this though.
Well,
Let's see. Add and what else could we add now that we have this? We could have public void add to start, right? Int x. What would that look like? Oops. Just a call to add at index, but not at the end. At where? 0. Still work. Looks like it still works. Let's go ahead and make sure it works by adding something to the beginning. Say what?
did you actually add to end?
We did use add to end up here. So here we'll go ahead and add to start. And we'll add 144 and spell it right. There we go. And then print it out again. And so now I should expect everything shifted down with 144 at the beginning.
You just put the size.
Dang it. Thank you. There, 144. Ooh, yeah, 144 at the beginning. Everything else is shifted down. All right. I'm convinced that it kind of works. Let's see. Kind of, yeah. I think that there might be an error here in our increased capacity, though. I'm not sure how to reproduce it at this point. Let's see. I know. Here, let's just keep adding things at the end, at the end, at the end. 1,000. 1,001, 1,002, 1,003, 1,004. Okay, keep going. How much stuff is in there already? 13, and then I added 5 more. So I want 5, 6, 7. There we go. 5, 6, 7. Save that and run it. Oh, okay, it's still working.
We did it by 10.
Say what?
When we added on to it, it increased by 10.
Yeah, I was hoping that, let's, oh, you know what? Here, let's erase all this. And now I know how to reproduce the error that I'm thinking of. Add element at index. And then I'll say l.getSize. And the element will be 101. There we go. Oh, no? Okay. Add a bunch of copies. Nope. All right. I was not able to reproduce the error that I'm thinking of, but this is really suspect right here, right? Add element at index. I want it at the last index, right? Oh no, I did it right. If it's greater than size, okay. No.
What were you expecting?
Okay, so here's the error that should be manifesting, but I don't know off the top of my head how to do this. That if it's already full, we can't shift stuff down, right? But we don't do that until we get here. So yeah, I think we're fine. But this morning I'd have to go back and look how I did it this morning because I was able to reproduce the error there and fix it. Anyway. Let's do some other stuff now. We put stuff into the list. How about getting stuff out of the list? What might that look like? Most generally. Public int get element at index. Int x int index, sorry. I'm not putting stuff in, we're just getting stuff out. Can I just simply return this.array at index? So let's do some error checking, right? What does that error checking look like? If it was an exact copy pasta, yes, I would say do some error checking. Put it into a method. But I'm going to draw your attention to this fact right here. The index is greater than size. If there are 5 elements in there, what could you ask for? 0, 1, 2, 3, 4. Could you ask for index 5? Index size? No. So, if it's greater than or equal to size, that's also an error when you're getting stuff out. When you're putting stuff in, that just means that you're putting it at the end. But when you're getting stuff, then yeah, definitely wrong. Get the last element, what would that look like? Just call this function on the size minus 1. Get the first element, you could do that as well, right? And that sets us up for, stacks and queues, implementing them with some sort of a list. That looks good. But now what is this good for? Now let's go back to your observation from before. Let me go ahead and try to put a string in there. l.add to start my name. It's not even going to compile. Why? What is this list good for? Only integers. So far we have good encapsulation. We've hidden the implementation, the fact that we're using an array to store stuff from the outside world. We've protected it by making certain things private and other things public. We've made it abstract so that you don't have to worry about the details of increasing the capacity, error checking, et cetera, et cetera, et cetera. The last part here, though, is polymorphism. where I don't want to write a list for doubles, a list for strings, a list for integers. I want to write one list to rule them all. That means I need to parameterize it, capital T. Okay? Over here, this list will now be a list for integers. And it's okay to put integers in them. The compiler says you can't put strings in there because that's a list for for integers. That's all right. You can have a list for my list for strings. Right? Names is equal to new my list parameterized. And now names dot add to start. I can add my name. I can add Joe. I can add Jane. Or can I? I parameterized it, right? I didn't take care of everything else. Add to start still only takes integers. All right. So we need to change more stuff here. It's not just integers. This should be an array of what? Doubles? No. Strings? No. If it's parameterized, then the type is also a variable. It's an element of t's. What are t's? I don't know. Who cares, right? I'm just holding this stuff. You ask me to put it. I've got a bag. You give me another t, and I'll put it in my bag. You ask for a particular element in the bag. I will give that element back to you. You don't have to know that. What is this? What is a t? I don't care. I put stuff in and I take stuff out. Right? Now, that's not going to work. This is because of the way that parameterization was added to Java. It was added later. And there's no way that you can tell, there's no way that you can't have an array without a type. You can have an array of any type of objects if you want. That's still not going to work because you need to, well, here's the solution. Typecast it, right? There we go. That'll work. It's still a warning because I'm using a raw type. You've got strings, you've got integers. I don't care. They're both objects, so from my perspective, everything's an object. Right? And typecasting it to type T is actually necessary, but at the end of the day, I don't care. Because what I'm going to do is I'm going to change the other methods so that if T ends up being an integer, you can't give me a string. The compiler will reject you at compile time rather than at runtime. There's also another issue here that when I had int, the Java virtual machine knows that an integer takes 4 bytes. If I had double, the Java virtual machine knows that doubles take 8 bytes. If I have t, it doesn't know what t is, therefore it doesn't know how many bytes it takes. So I am forced to use an object because it does know how many bytes an object reference takes. I think 4, but I'm not sure. Right? I just typecast it to that type. Now it's an array of integers. Now it's an array of doubles, whatever. You can ignore the warning, or you can put an annotation up there that says, I ignore the warning, suppress the warning. Right? Unchecked types. Okay? Some problems now, though. Get element at index. It's no longer returning an integer. What is it returning now? T. That's happy. Complaining because you can't assign an integer, x, to an array of elements of type T. That's okay. We're parameterized. Right? Like there, there, and there. And that should be enough. Right? You thought that those were up. Where?
Get element at index. Oh.
That's the return type. Right? Did I have to change any of the substantial lines of code? No. That's what the beauty of parameterization. That's the beauty of polymorphism. Write one thing and then use it for any type. Right? And over here, you see that it will work. Right? Let me go ahead and actually print it. Names. And now it'll be Chris, Joe, and Jane at the end. Yeah. All right. So, what else might you want out of this? What, like some Well, first of all, we didn't do all the CRUD. We didn't give you a way to remove elements or replace elements or something like that, but you could certainly do so. What would remove element look like? If I've got 5 elements in there and I want to remove the guy in the middle, do I want to leave a gap? I want to shift things down. What would replace items look like? I want to replace 10, 20, 30 with 42. Right? One way that I could do that is simply, here's 42, replace whatever's there, I don't care. Or replace whatever's there with this that I'm giving you, and then give me back whatever was there so that I can exchange, right? You can do this dozens of different ways. You can add as many methods as you want to make it as flexible as you want. At the end of the day, though, you don't implement MyList. You use ArrayList, right? I'm just showing you what it looks like. There is a cost to this increasing of capacity. It does, if there are 1 million elements in there, you are going to copy over 1 million things just to increase the capacity slightly, right? If you do that a lot over and over and over again, then you're doing, how did you get there to begin with? You had to copy things in increments of 10 up to 1 million. So in other words, it's kind of like 1 million times 1 million. What are those? 1 million times 1 million operations. Many, is that quadrillion or quintillion? I don't know. I always like to quote the old movie Once Upon a Time in the West, right? He goes, wow, that contract must be worth a lot of money, thousands of dollars. This is the Old West. He goes, a lot more than that, thousands of dollars. And he goes, they call them millions. He goes, millions? Because he'd never heard of that word before. I don't we can't admonish him because we don't know what million is without writing it out and figuring it out for ourselves. So there might be other things that you want to do, like say batch operations. Right. Add several elements at once. Maybe you want to support a copy constructor, a way to copy one list into another list. Copy constructors. Right? What else might you want? What do you want in a list? If you were to go shopping for a list, what would you want? Oh, good. Finding, searching, right? A list. What would that look like? At least the way that we've got it right now. Start at the beginning, search until you found the needle in the haystack. We call that. That would be starting in the middle and then going left, right, right? So linear search, right? So finding or searching an element. What would it also look like now that we've parameterized it? You're not searching for 42 anymore. I don't know what, I'm the list now. I don't know anything about 42. I don't know anything about integers. I don't know anything about doubles. I don't know anything about strings. You got to give me something else to tell me that when I hold up an element of type T, that's the thing you're looking for, right? What is that other thing? A comparator. Now I can iterate through the first element. Comparator, is that equal to what you're looking for? No. Second one, is it what you're looking for? No. Third one, is that what you're looking for? Yes. Okay, now I'm done, and I give you that element, right? What time is it? Yeah, 10 minutes. Do we want to do it really quick? See what it looks like? Okay.
Is this what our next phase is going to look like?
Something like the last phase. Last phase, you will have to implement a sorted list, but it maintains an ordering. So instead of allowing somebody to arbitrarily insert something, here you go. It maintains an order so that the way that I did it here was 10, 20, 30, 40, 50. If you add on in 30, or 33, it should put it where it belongs. Right? And the way you want to do that is with a comparator. Right? So I'll have a private comparator. What's this a comparator for? Elements of type T. What's it called? I don't know. CMP. Short for comparator. Right? I need to bring it in, of course. Right? And I will have another constructor that takes a comparator for things of that type. Right? Because if you want to, then you could rely on the natural ordering and assume that they're comparable, or you can use a comparator here, or you can just ignore it and say, all right, if they call that method that requires the comparator, I'm going to throw it back at them that they called this constructor, so they were never intending to use the comparator, so that's on them. Right? There are lots of ways that you could design this. We'll go ahead and take this as a comparator, though. This.cmp equals to cmp. And now let's look at a find method. Public int. What should we? No, I didn't put int because I forgot that we had parameterized it. How would you want linear search to work? Okay, it could return a t value, or you could even give even more information of, yeah, I found your guy. It's right there at index int. So index of. And then what we'll do is we'll take an element of type t, the key, because we're searching for a needle in the haystack. If you want to call it a needle, right, go ahead, but we'll go ahead and call it a key. For int I equals 0, I is less than this dot size, I plus plus. We're simply iterating over the elements of the array and asking the comparator, this dot cmp, dot compare the key to the ith element, this dot array sub I. Now remember the contract of a comparator. A comparator will return something negative if A comes before B, something positive if A comes after B, or the thing that we're interested in, 0 if they're equal. So if this is equal to 0, then we can return the index of where we are right now. Right? What if that Chris, Jane, Joe, George is not in the list? What should we return back to them? We could return a negative value, right, as a flag value. We could throw an exception. We couldn't return 0 because that would be saying it's located at index 0. Right? Or we could give even more information, and this is what Java does with linear search and binary search. If it had existed, it would be at index x. I will return negative x. Cool, right? Negative x plus 1 or something, because you can't, it belongs at index 0. I need to go negative 1. Right? So negative index minus 1. And that's where it is. If you wanted to insert it, you could take that absolute value and insert it there, and that's where it would be. Right? If it were ordered or something like that. Right? All right, let's see if this works. System.out.println. Index of Chris is plus names dot index of Chris. That's not what I want. There we go. Now what's going to happen here? We still have 2 minutes so we can fix it. Null pointer exception. Why? I never gave it a comparator, right? So what we could do is we could do some error checking up here. If this.cmp is equal to null, then throw a much more expressive condition, like throw a new illegal state exception. You didn't call the right constructor. Jabroni. Right, there we go. And there we go. Call the right constructor. Yeah. Yes, so you could, oh, good. So you could use the dot equals method, but then it's on them to overload that method. So that's a third way that you could do that. You could use a comparator. You could force them to only allow, you could parameterize it to only allow comparable, naturally comparable things like integers and strings and stuff like that. Or you could go a third way of using the dot equals method. With the dot equals, you do have, now it's built in on strings, it'll work, integers, it'll work. But if you've got like a bank account or a sale, this sale is not necessarily equal to this sale unless you override the equals method to say, what does it mean for two sales to be equal? Well, they have the same code. That's all it means to be equal. Or they have to have the same code and the same salesman and the same customer, dot, 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 dot. And only then are they equal. And you could go that way too. I wanted to show you this way because this is probably what you're going to want to do in your project. Right? So undo that. Let's go ahead and see what it looks like. A new comparator or something like this you'll want to do for your project. String, and then define it in line here. Yes, you can. No. New comparator. Fine. Public int compare string A string B. Return A dot compare to B. Now are you happy? All right, darn it. Comparator for T. I will save you over here. Comparator of type T of string equals that stuff. It was probably complaining because I never imported comparator. Now that that's there, CMP, now I should be able to pass it in. There we go. And now it won't gripe about it. Index of Chris is 2. Is that right? Oh yeah, because add to start. Chris, add to start. Joe, add to start. Jane. So I ended up at 2 instead of, I thought I would be at the front, but I wasn't. Right. Cool? Yes. All right, so that is index-based lists. Are there other types of lists? Yes, that's where we'll go on Tuesday. There's what's called a linked list that has no fixed size at all. Instead, you've got nodes. Those nodes refer to other nodes. And then to traverse through that list simply means that you go from one node to the next node, next node, next node. Right? And you don't have to have contiguously allocated memory at all. Right? All right, looks like the live stream survived the entire time. Excellent.